We discussed in this video about tooth functions. And in this video, we are going to focus on set 0, 1, in other words, the integer 0, 1, on which we are going to make operations such as additions and subtractions. But we are going to think about 0 as corresponding to false in terms of logical formulas, and 1 is going to correspond to true in terms of logical formulas. And in fact, we are defining the set nu n to be 0, 1 to power n. In other words, we define this set to be the set of vectors of n dimensions over set 0, 1. So ai, all the values ai are in 0, 1 for all I between 1 and obviously the size of nu n is exactly 2 to the power n, which is useful to know when we discuss about tooth tables. We define tooth functions so a tooth function of n variables is going to be simply a function phi defined on nu n with values in 0 and 1. We are going to also denote by fn the set of all tooth functions and variables. And I'm going to show that this set of functions becomes a Boolean algebra with a number of operations that I'm going to define next. And these operations are going to be familiar to you. I'm going to talk about disjunction, conjunction, and negations. And you have seen this before when you discussed about operations on logical variables. This time I define them on functions, but your intuition is going to serve you well. We will define them in such a way that when I take these functions on one particular element, they are going to come down to the usual definitions of disjunctions, conjunctions, and negations. So here is how I define these operations. If I take two elements of this set, meaning I take two tooth functions of n variables, I'm going to define their disjunction, and I'm going to denote it as usual with phi or psi. This is obviously also a function of fn, so also a function of n variables, and this is defined as phi or psi. The value of this function on vector v is going to be exactly the maximum between phi of v and psi of v. So remember, phi and psi are functions that take values in 0, 1. So obviously when I apply maximum between two numbers that can only be 0 and 1, the result is also going to be just 0 or 1. So this is a well-defined function. And I define the conjunction, denoted like this. This is also a function of n variables. And the value that this function takes on a vector v is going to be exactly equal to minimum between phi of v and psi of v. And with the same argument, we can also see that this is a well-defined function. It takes values in 0 and 1. And I'm also defining the negation of phi, and I denote it as usual like this. This is also a function from fn, and the value that this function takes in vector v is defined as exactly 1 minus phi of v. And again, notice that phi of v can only take value 0 or 1, and obviously 1 minus this also takes values just 0 or 1. So this is a well-defined function. And just to make the point that these are indeed your usual definitions for disjunction, conjunction, and negation, even though they might look a little bit different in terms of the definition. I'm also going to introduce or remind you of the concept of truth tables, and this is going to be useful to us when we prove properties about truth functions. And when I do these truth tables, you are going to see that these definitions indeed correspond to the typical way you define disjunction and conjunction. So what I mean by a truth table, I mean that you really are going to describe all the possible values that a vector v can take, and then you say what the value of the function is for each one of these combinations. So in our case, we want to think about what the definition of this function could be, and that depends on its two arguments. So if I think about the value that phi of v can take and psi of v can take, each one of them can take value in 0 and 1. So that means that we have 4 possible combinations, and these are the 4 combinations. And then I think about what I define to be phi or psi in V. And so according to our definition, this is the maximum value between phi and psi. And I'm looking at this, and in this case, they are both 0. So the maximum between 0 and 0 is obviously 0. But in this case, is at least one of them is 1. In this case, both are 1. So the maximum between values that are either 0, 1 or 1, 1, obviously the maximum in all of these cases is going to be 1. And now you can see that, in fact, the way we have defined disjunction through the use of the max function is exactly the way you would normally define disjunction of two logical variables, meaning that it's 1 everywhere except in the case where both variables are false. And I can also think about the values that the conjunction can take. And remember, we have defined this through the mean function, so it's minimum of phi and psi. And so that means that if at least one of them is 0, the minimum is going to be 0. So it's going to be 0 everywhere in these 3 cases. But here they are both 1, so the minimum between 1 and 1 is obviously 1. So if you think about 0 corresponding to false and 1 corresponding to true, then you get the usual definition that the conjunction of two variables is exactly 0, except in the case where both variables are 1. And that comes also from our definition of the conjunction through the use of function mean. And the same can be done for the negation. So this time I only have one dependent on defining the negation. So I only have to think about the values that phi of v can take. So there are only 2 possible values, 0 or 1. And the definition for the negation was 1 minus. So in this case, it's going to be 1 minus 0 equals 1. And in this case, is 1 minus 1 is equal to 0. So this also corresponds to the usual way you define negation, meaning it's true exactly in the case when the variable is 0, and it's 0 or false exactly in the case when the variable that you apply it to is true. And I'm also defining now 2 constant functions, and I define them like this. So this is going to be one function I define, and this is going to be defined to be 0 or false, if you like, for all v in nu n. And I also define another constant function that I just denoted like this. And the way I define this is that this function takes value 1 for all v in nu n. So now we have all we need to prove the result that I wanted to prove, meaning that this set of truth function becomes a Boolean algebra. So really the lemma that I would like to prove is that the set of these functions, truth functions, when I equip it with disjunction conjunction and with the constant elements defined here. Obviously I forgot, and there should be also the unary function, which was negation. So this set with these operations and these constant functions, this is a Boolean algebra. And this is true for any n. So meaning this is true for any truth function, no matter how many variables it has. So to prove this lemma, so again, we want to prove that Fn with disjunction, conjunction, negation, the 0 element and the 1 element, this is a Boolean algebra. And to prove this, we have to prove, so this is the same as saying we have to check that all the conditions B1 to B10 in the definition of a Boolean algebra hold. So we have to prove this. And I'm going to show you how the proof goes for some of them, and I will start with B1. So for B1, what we have to prove is that the disjunction is an associative function. So in other words, what we have to show is that phi or psi or psi is exactly equal to phi or psi or psi. And this is true, we have to show that this is true for any functions phi, psi, psi in Fn. And here is the argument why this condition holds. If we think about what's the value that this function on the left-hand side takes for a variable v, so if we think about who this function is for some vector v of n variables, according to our definition, this is the maximum between, on one hand, phi of v, and on the other hand, the result of this function, which is really the maximum between psi of v and psi of v. Of course, we know that if we take the maximum in this way is the same thing as taking the maximum simultaneously among these three values, phi, psi, and psi. Now I can make the same steps going towards establishing this right-hand side. So I can also say that obviously this is the same as taking first the maximum of these two elements, and then the result, I take the maximum between the result and the third element. And this is exactly the, according to our definition, that's exactly the value that this function takes for vector v. And this obviously holds for all v in mu n. So that's the way to establish B1, and B2 is exactly similar. So B2 aims to establish that the conjunction is associative. So in other words, we would have to prove that phi and psi and psi is exactly equal to phi and psi and psi here. And to prove this, and obviously this is to be proved for all phi, psi, psi in Fn. So to prove this, we have a very similar argument as in this case. We just recall what the definition of this function is for a vector, for an arbitrary vector v. So in other words, we think about what the value of this function is for a vector v. And this, according to the definition, our definition of conjunction, is exactly the minimum between, on one hand, phi of v, On the other hand, the value of this function, which is also a conjunction, so it's again a minimum between psi of v and psi of v. And the minimum of these values obviously is the same as taking the simultaneous minimum of the three values, phi of v, psi of v, and psi of v. And again, going towards establishing the right-hand side, I just realized that this is the same as taking first the minimum of these, and then the result, I take the minimum between the result and the third one. So in other words, this is the same as taking minimum between first minimum of phi of v and psi of v, and then taking the minimum between the result and psi of v. And that's exactly how the function phi and psi and psi is defined for vector v. And all of these considerations, they obviously hold for any value of v in nu n. So that establishes B2. And the rules B3 and B4 obviously hold because really the maximum and minimum are commutative functions, so that makes also the conjunction and disjunction commutative functions. And to prove now B5 and B10, the easiest way to go about that is to really draw the truth tables of those functions. And I'm going to show how to do that for B5. You also have in the lecture notes the explanation regarding B6, but here is how it goes for B5. So for B5, what we need to show is that phi or psi and psi, this is the same function as phi or psi and phi or psi. So this is what we need to prove. And so we are going to have a truth table where we think about the values that this function can take for any vector v, depending on the values that phi, psi, and psi can take. And then we will do the same for this big function in here, and we are going to show that the values are the same. So for this truth table, we have to think about what's the values that phi of v, psi of v, and psi of v can take for an arbitrary v. So we start with the values that this function can take. And since each one of them has two possible values, obviously in the combination we are going to have 8 possibilities. So all of them 0, one of them 1, or two of them 1, or all of them 1. And somewhere here at the end, I would like to see that on one hand, this right-hand side is calculated. So on the right-hand side, eventually I will get to calculate the value of this function on the right-hand side, meaning phi or psi and phi or psi for vector v. So that's what I would like to get on this last column. And on the column before that, I would like to see what are the values of this function. So I would like to get to calculate eventually phi or psi and psi for vector v. And I'm going to calculate this step by step. I'm just drawing also the horizontal line so it's easier to see how these values propagate. So to calculate this function, I first need to calculate the values that the conjunction psi and xi can take. So I'm going to calculate that one first. So psi and xi applied to V. And to calculate this, I'm going to focus on these two columns, psi and xi. And by the definition of the disjunction, this is really going to be everywhere 0, except in the case where both pi, psi, and xi are 1. So here is going to be 1, and also here is going to be 1, but everywhere else is going to be 0. So once I have this column calculated, I can now calculate the values of this function, and to do that, I need to focus on the values of phi and the values of this function that I just computed, and it's going to be a disjunction between these ones. So according to the definition of the disjunction, this function is going to be everywhere 1, except in the case where both this column and that column has 0. So it's going to be 0 here because this one is 0 and that one is 0, so that's going to be a 0. And this one is also 0. This one 0 and 0, that's a 0. 1 and 0, that's going to give us a 1. 0 and 0 or 1 is 1. 1 or 0 is 1. 1 or 0 is 1. 1 or 1 is 1. So now I calculate this component and I calculate this component, and then eventually we are going to calculate the conjunction between them. So first I calculate phi or psi applied to V, and to do that, so it's phi or psi, so I focus on column phi and the column for psi, and the values is going to be 0 or 0 is 0, 0 or 0, 0, 0 or 1, 1, 1 or 0, 1, 0 or 1, 1, 1 or 0, 1, 1 or 1, 1, 1 or 1 is 1. And then I calculate the values for this function, which is phi or psi. There were some parentheses missing here. So to calculate this one, I'm going to have to focus on the column for phi and the column for psi, and then it's going to be 0 or 0 is 0, 0 or 1 is 1, 0 or 0, 0, 1, 0, that's 1, 0, 1, 1, 1, 1 is 1, 1, 0, 1, 1 or 1 is 1. So now when I have these values, I can now calculate this column, which is going to be a conjunction between these two columns that I just calculated. So this function is going to be 0 and 0, that's a 0, 0 and 1, 0, 1 and 0, 0, and here everywhere is 1 and 1, which gives us 1 everywhere. Now we can just conclude by comparing these two columns that they are exactly the same everywhere, 0 on the first 3 rows and 1 on the rest of these rows. So we just observe that these are identical, which is exactly what we needed to prove that these two functions are equal. So that means that we have just established B5. And to establish B6, and in fact all the other ones up to B10, similar calculations can be done.